So, yeah, because I remember they were trying to get us to put part of when they built Madrone Hall, how to get that incorporated into some little educational thing, because they would have got them some lead points. So it's more than just the final functioning. I know that.
I think that leads level 4.
Yeah, it's not the top. Yeah, I remember that. Yeah.
You never went into one in L5 community. Great.
Yeah, it's not.
L5.
I don't know what an L5 is.
Neither do I. Great, you're supposed to, you got distracted.
Ask him about singularity too.
No, we already did talk about it. We didn't discuss anything that we're supposed to discuss. And we have lab tomorrow about oscillation.
All right, so here we go. So here's the list of stuff that'll be on the test. So simple stress and simple strain, axial and shear. Finding internal forces and stresses when multiple forces are applied. That's when we had like a long bar with different forces on it. You cut the bar or take one whole side or the other to find the internal forces, that stuff. Yeah, it was. Okay, stress strain diagram, find the modulus of elasticity, proportional limit, elastic limit, yield stress, ultimate stress. What's a permanent set and what's yielding? Where does the sample strain harden?
Is that going to be like identifying it on a graph? Or?
Yeah, or plotting it up or doing something. Yeah. Modulus of rigidity is the shear modulus. Poisson's ratio is the, this thing. Okay, modulus of rigidity is G. So then you got delta is PL over AE. You should be able to do that when you've got multiple forces. Okay, statically indeterminate problems. So you want to be able to recognize those and then do the statics and then do the strengths to solve them. Temperature induced stress and strain. And then we did the axial and then the biaxial stuff. Okay. Yeah. Question?
I mean, I have a question, I just don't know how to ask it yet.
Okay. Okay, vocabulary, stress and strain, tension, compression, which can be tensile and compressive, shear stress. Deflection is deformation, is displacement, is delta. They all mean pretty much the same thing, okay? Yeah.
The axial loading and the biaxial loading, that's like the uni.
Uniaxial is axial, yeah,
okay.
And biaxial.
And then so the axial loading, is that the one where you go from the vertical to the plane?
No, the uniaxial, you go from the standard cross section to the plane. Biaxial, you go from the vertical. Okay.
Is the Moore circle on there?
Yeah. It's under biaxial. Yeah.
And do we get the full 2 hours for the test, or is it?
No, I'll probably make it about an hour and 50 minutes.
All right.
Okay.
You're still gonna have lecture.
Yeah, afterwards we'll go over some new stuff. Oh, that's what's going on. Okay. All right, and then I've got some just examples there. If I can get to these dang things. Discard. So for those of you online, these reviews are available online under the test downloads, I think they're called. Let's see here. Where am I? String star points. Okay, so there's the first one. So that's just a normal stress strain curve. Is shown for material. Use the curve to determine the modulus of elasticity. Okay. I think I got the answers on there. We can go over these on Friday if you want. Okay, find the deflection of point C after the load shown or applied. So what you're going to do with that? Yeah, make the cuts. Find the internal forces in AB and then BC and then PL over AE for each section. Add them up. Initial dimensions of the bar are shown at 30 degrees C. There's no stress at 30, then it goes up to 42. Find the maximum normal stress and maximum shear stress in the bar. So when the temperature goes up, the bar is going to try and lengthen, but the walls won't allow that. So the bar will be in compression or tension.
Is this where we have to find the new equilibrium?
It's not quite that complicated, no.
Because it's going to expand and then.
Yeah, the walls aren't going to change.
Assuming the temperature is going back down, so it's not going to compress again.
It's
Well-
it's gonna want to go delta distance in the wall, but.
Wall will not allow that.
Back, right?
Right,
Yeah.
and so that's gonna create, the wall's gonna push back on the metal, so it's gonna create a compression, correct?
Yeah, right.
Wall on.
Yeah, it's trying to get longer, but it can't. Yeah. So you're going to find how much longer it wants to get, and then that's the delta. In this case, there's no gaps or anything. Once you got delta, you can back into the load. P, using delta as PL over AE, you can figure out P. Yeah, okay. Y'all remember that?
Yeah,
We
and
did.
Do you wanna go from corner to corner to find hypotenuse?
No, not on this one. I didn't ask for it. So just looking for the stress.
Okay.
Okay. Mm. This one, find delta of point A. Okay. What you gonna do on that one?
Well, you have to find the delta again.
Yeah.
We did that in class.
Yeah,
It's
no,
page
I
200.
remember, I can draw the picture
Mhm.
both, what's happening.
Oh, this is where, yeah, the, normal plane,
Yeah, you guys don't want to look at this one every Friday. We'll go over it.
I can't remember how to do it, but I know we've gone over it.
Yeah, we have. Yeah, okay. So, have a look at that, okay? How about this one? That one's pretty simple. Once you know how to do it, it's
Yeah.
quick, but you have to know how to do it. We got a tank on those supports. We want to find the force in the middle support, and we want to find delta.
So you find the sum of the forces.
Oops, hang on. Having trouble here. There we go. So what is this? What's the word for this that describes what it is? Close, but not quite. It's more than just equilibrium. It's statically indeterminate. Yeah, you can't get this with statics. You got to do statics and strengths with this thing. Okay.
So this is statically indeterminate?
Yes. Yeah. All right. So you got to use statics, but then you also got to use PL over AE. Okay. We're good. Okay, here's another Morse circle you can practice on. Okay. Should say plane CD there. I don't know if it does or not, but it ought to. I said plane AB, and then I said it's CD points, but it's plane CD. It's a typo. Now, I'll definitely give you more circle on this test on Monday to do. You're going to want to use trig when you do it, okay? So I give you the answers there. Should be able to work through that, I hope, but we can go through it a little bit. In class, is that the last one, or I think I got another one there. Okay. Find the normal stresses on plane AB. And what would it look like if it broke? So what you going to do on this? What's the first thing you're going to do? You're going to...
Well, we're given our angles already.
Yeah, that's an important statement. You're given the angle, so don't go all...
don't find the tangent.
Yeah, don't do the tangent 2 theta. Don't add 45 to get a shear angle. Don't do any of that. Just,
Find the principal stress.
yeah, don't find the principal stress. Yeah, just find that angle, plug it into the formula, and tell me what the stresses are on the plane. That's all you got to do on that one, okay? So don't make it hard. Just if the question is find the stress at a given angle, just plug the angle into the formula and get the stress. Okay. Yeah, those are just some old test questions. How much was that?
No, Moore's circle was 30 points, and
Oh.
then the one that don't make it complicated, 4 points.
Oh, that was only 4 points?
Yeah.
12 too.
Oh, it's 12 and 4.
Sorry,
Yeah.
16 points. 16.
Yeah, there we go.
I was like 30 to, and then 4.
Yeah. No, okay, let's just look at one other thing, then I'll let you go here. But so we'll go over that Friday if you like. Okay. Okay, just the last little thing I want to mention is on that homework that I handed back today. This here. But it's the stuff that I handed back today, like 201. Some of you were using that radical formula, okay? And just be a little careful about that. Some of you were using, I don't know what number it is, but I guess 202. Yeah, let's look at 202. So this is finding the principal stresses. So the way I approach these is I find the angle first. And then when I've got the angle, I plug it into the general formula. That way I know which stress acts at which angle. I don't use that radical formula. The problem with the radical formula,
Oh, it doesn't give the angle.
it doesn't tell you which stress acts at which angle. So I don't use formulas 28 and 29, generally speaking. Okay? And the problem with those formulas is I know what the stresses are, but I'm not sure which direction they act. Okay.
Can you not use the idea of what angle we figured out to the corresponding external forces?
You could, yeah, you could on this.
Like if we
You could, right, that's how you do it. If you want to use the radical formula, you got to have a pretty good eye and look at this and get it oriented properly. You could do it that way, yeah. I don't teach that so much anymore because it's a little too subjective. What I've landed on is more find the angle, plug it in.
Right.
Don't, keep it simple. That's kind of how I do it now. But you can use that radical formula, but you got to eyeball it as far as making the sketches and get it right.
That's the thing. You get it right.
Yeah, that's true. That's true. And especially on the shear, because I noticed a lot of you were using that formula. I think it was 29 on the shear. And then I'm thinking, well, okay, that's nice. You got the plus and minus shear values, but which one acts on which plane? And I don't know if you all really knew how to get that done. It's the same sort of concept. Although there's a little bit more to it, but the safest way to do it to find the maximum shear is just find the angle, add 45 to your principal angle, and then plug that into the general shear formula. That way you'll get the sign of the shear at a given angle. It's very simple to draw it up if you need to do that. All right. So if you want to make sketches, beware of those formulas 28 and 9 because they make it a little bit more challenging. That's all I want to say about that. Okay. Now, if you're good at it, you can do it. You can use them. But the simplest way is just get the angle, plug it into the general formula. Okay. And that holds for both normal stress and shear. All right. Good to go on that. Okay. Call it good. Yeah, just a second.